Welcome to the video for section 3.2. In this video, one of the points I want to make is that the measures of center don't always tell the whole story when it comes to a data set. Consider these two data sets that come from two different populations. I'll call it data set number 1 and data set number 2. What's similar about these data sets? What's different about them? Well, one of the things you might notice right away is that data set number 2 has more numbers in it than data set number 1. Data set 1 has 6 numbers, data set 2 has 8 numbers. You might also notice that the numbers in data set 1 are spread out, going from the 40s up to the 90s. Data set 2, the numbers are more clustered together, all in the 60s and 70s. Those are some differences between these two data sets. In terms of similarities, well, what's similar about these might not be as obvious as the differences, but if you were to calculate the mean for each of these data sets, you would find that they have the exact same means. In both cases, the mean for the data set is 70. So if the only way that we describe the data was with the mean, we might think that we have two data sets that are very similar. And while they are similar in that aspect, you can see from the numbers that are in the data sets that they're actually quite different. So we need to describe more than just the center of our data in order to get the whole story about what's going on in a data set. But let me show you two pictures just to illustrate what's really going on here with these two data sets. I've taken each data set and I've plotted the numbers on a number line. Notice how the numbers in data set number 1 are kind of all strung out along the number line, whereas the data in data set number 2 is all clustered together. We want to have some kind of way of capturing how spread out the data is in a data set. It's not enough just to say that the mean is 70, because you can see that's the case in both of these data sets, but they're really quite different. We also want to have a way to talk about how spread out the data is, because that's another important feature or characteristic in the data. These ways of describing how spread out the data is in a data set are known as measures of variation. And that's what section 3.2 is all about. We're going to learn 3 different ways to measure the variation in a data set. Now, the second and third way are very closely related, so I almost call it 2 different ways. But you could say it's 3 separate ways of measuring this. Okay, the first way is with the range. The range is a very quick and easy calculation. It's just the maximum minus the minimum. You can see for data set 1, the maximum was 95, the minimum was 44. Subtract, you get 51. For data set 2, the maximum was 75, the minimum was 65. Subtract, you get 10. Now, it seems like the range does the job that we want it to do. For data set 1, where the numbers are spread out, we get a big result, indicating a lot of spread in the data. For data set 2, the numbers are clustered together. We get a small result, and that indicates that the data doesn't really have a whole lot of spread. Now, the only problem with the range is that it only considers 2 values in the data set, and they happen to be the minimum and the maximum. If you have what's called an outlier in the data set, it could throw the result off and give you a misleading picture. Let's say we had another data set. I'll call it maybe data set number 3. Let me draw a number line that would represent this data set. Okay, so let's say we've got another number line here. And let's say that the mean for data set number 3 is also 70. So right here in the middle of the data set, we'll have our sample mean or population mean. If we're dealing with population data right there in the middle. So that represents our mean. Now let's say that for this data set, we've got a whole bunch of numbers that are just all clustered right here close to the mean. Let's just say there's like, maybe 98 numbers all clustered. I'm not going to draw all 98 dots, but let's say there's, like a whole bunch of them clustered here. And then we just had one really high value, one really low value. We would call those numbers outliers because they're numbers that don't really fit with the rest of the group. We're going to talk more about those in the next section. But for now, just think of an outlier as a number that doesn't really fit with the rest of the group. Well, if we were calculating the range here, the maximum minus the minimum, we would get a pretty big number, suggesting that the data in this data set is all spread out. But that's not really the case. I would say the numbers in this data set are more or less clustered together. Okay, the vast majority of them are. It's just these two outliers kind of give us a misleading picture because the range only factors in those numbers. It doesn't allow all the numbers in the big cluster in the middle to contribute to the result. So the range is a quick and easy calculation, but it's got its disadvantages. So ideally, we would like to have some other way to measure the variation that doesn't have this kind of problem that the range has. So standard deviation is another way that we can measure the variation in a data set that doesn't have the same problem that the range has. Now, standard deviation, this is not a 100% technically accurate definition for it, but if you think of it in these terms, it will kind of help you get your mind around what the standard deviation is kind of sort of doing. You can think of it as an average distance to the mean. Now, to calculate the standard deviation, we typically calculate something called the variance first, and then we go one step further with it and actually get this standard deviation. So variance by itself is a measure of variation, but it's really just a stepping stone to get to the standard deviation. So that's why I said we've got three different ways to measure variation here, but these two, variance and standard deviation, are tied very closely together. Okay, so let's talk about how we might calculate the standard deviation here. So if I just list all my numbers for data set number 1 in a column like this, we've already talked about the average is 70. If I wanted to think about an average distance to the mean, what I might do is take each number minus the mean. That's what I've done here in the middle column. I've taken 95 minus 70 and got 25, 44 minus 70 got negative 26, 80 minus 70 is 10, and so on all the way down the list. 60 minus 70 is negative 10, 93 minus 70 is 23, 48 minus 70 is negative 22. Now, if I wanted to get an average distance to the mean, I would just add these numbers up and divide by 6. But when I add them up, I get 0. 0 divided by 6 is 0. So that would suggest that there's no variation in this data set, which obviously isn't the case. Okay, the problem is when you take each number minus the mean, you get this mix of positive and negative numbers, and they should always add up to 0. Because remember, the mean is that center of gravity point. And what it means to be the center of gravity is that when you add up these numbers that represent how far above or below these numbers are from the mean, you're always going to get 0. So it's the fact that we've got a mix of positive and negative numbers here that's kind of messing up the calculation. Now, there's two different ways that you can deal with this problem. One way is you could take the absolute value of all those numbers, right? So instead of having negative 26, you could just call it 26, representing a distance of 26 away from the mean. Okay, it's not really a big deal for us to say that this number is below the mean by 26 inches. We just care that it's 26 inches away. So let's forget the minus sign that tells us this number is below the mean, and let's just call it 26. And same thing, we can just call the negative 10, 10, and the negative 22, 22. Okay, if we applied the absolute value to every number in that list, the positive ones would stay positive, the negative ones become positive. That would solve the problem. We could average those numbers out and get an average distance to the mean. Okay, some people do that, and if you do that, that's called the absolute deviation because it's based on absolute value. But a lot of people in math just don't like to work with absolute value for various reasons. And so sometimes people will take a different approach here. And instead of taking the absolute value of all these numbers in order to get rid of the negatives, they square them. You might remember that if you take a negative number and square it, it becomes positive. So 25 squared is 625. Negative 26 squared is positive 676. 10 squared is 100. Negative 10 squared is also 100. So that's like negative 10 times negative 10, which is positive 100. 23 squared is 529. Negative 22 squared is 484. Now you can try to average these numbers out, so you can add them all up. That's 2,514. Divide by the number of numbers in the list, which is 6, and you would get 419. Now, the problem with that result is that the units are squared. So it's not really an average distance to the mean. That's more like an average distance squared to the mean. If we want to get back to an average distance to the mean, we would need to take the square root of that. Okay, well, that number, the 419, that's what we would call the variance. When we take the square root of it, that's when we get the standard deviation. So the symbol that we use for standard deviation is this population standard deviation, is this Greek letter lowercase sigma. Looks like a circle with a line off the front of it. Like I said, that's the square root of the variance. So we could say that the variance symbol is S or sigma squared. And you see the formula here, which is basically what I just worked through. Each data value minus the mean, square it, then add them up and divide by how many numbers are in the list. So that's like an average distance squared to the mean. Take the square root and you kind of sort of get an average distance to the mean. Okay, it's not quite because we squared and then square rooted, okay, instead of using absolute values. But the result is close enough that we could think of it in that way. So if we did the square root of the 419, then we would get 20.5 for the standard deviation of data set 1. We do the same calculation for data set 2, okay, which also had a mean of 70. So taking each number minus 70 and then squaring them, adding those numbers up, you get 78. 78 divided by 8, because there's 8 numbers in that list, would give you 9.8. That would be the variance for data set number 2, which you can see if you just compare variances. Data set 1, which is spread out, has a big variance. Data set 2, which has a lot of numbers clustered together, a little bit of variation, has a small result. So variance by itself does the job that we want it to do in measuring the variation. It's just that the units of the result have been squared, so they don't match the units of the original data. To get the units to match again, we want to take the square root and get standard deviation. So for data set 2, square root of 9.8 would be 3.1. Okay, so if you just ignore the minus signs, 20.5, which we said is the standard deviation for data set 1. I mean, that's kind of right in the middle of all these numbers if you ignore the minus sign. And what did we get? 3.1 for the standard deviation of data set 2. Okay, if you ignore the minus signs, 3.1 is kind of in the middle of all those. So you see it's kind of like an average distance to the mean. Not exactly, but you can more or less think of it in that way. So when you have a small average distance to the mean, that suggests the data is clustered together. When you have a big average distance to the mean, that suggests that the data is spread out. Okay, so that's population variance and population standard deviation. Now, what happens when we work with sample data? Well, first of all, we use a different set of symbols. We use the letter S for sample standard deviation, which means S squared would be sample variance. You'll find that whenever we work with sample data, we tend to use letters from the English alphabet to represent the statistics. When we work with populations, we tend to use letters from the Greek alphabet to represent the parameters of the population. So that's why we were using Greek letter sigma for population standard deviation, but English letter S for sample standard deviation. Now, the big difference here is whenever you work with the sample variance and calculate that, instead of dividing by n, you actually have to divide by n minus 1. And the reasons for that are beyond the scope of this course, but basically what happens is when you take a sample out of a population, it tends to underestimate the variation in the data. So your sample variation tends to be an underestimate of what the variation really is in the population. So to compensate for that, we end up dividing by a slightly smaller number to boost the result up a bit. That way, our sample variance kind of matches the population variance. So let me just show you an example here of sample data and how we would calculate the sample variance and standard deviation. Okay, so let's say we have this data set here, which comes from a sample. So these are all the X values in the first column. If we add them up and divide by 8, because there's 8 numbers in that list, we would get 17 for the mean. Okay, so our sample mean is 17. Add them all up, you get 136. 136 divided by 8 is 17. Take each data value minus 17. That's what I've done here in the middle column. 17 minus 17 is 0. 28 minus 17 is 11. 25 minus 17 is 8. And all the way down the list. That middle column should always add up to 0. Now, if you had to do any rounding with your mean, it might not be exactly 0, but it should be close. Now we're going to square all those values, which we've done here. Add those numbers up, you get 378. Okay, so 0 squared is 0, 11 squared is 121, 8 squared is 64. Add that up, you get 378. Now, because we're working with sample data, we're not going to divide that 378 by 8. We're actually going to divide it by 8 minus 1. That's the difference between population variance and sample variance. Population variance, you divide by n. Sample variance, n minus 1. So that would be 378 divided by 7, which is 54. That's the variance. Take the square root, and you get 7.3. That's the standard deviation. Which again, if you go back to the middle column and ignore the minus signs, what you would have are the distances to the mean, and that 7.3 is kind of in the middle of those numbers, kind of sort of representing an average distance to the mean. Okay, so just be careful when you are calculating variance and standard deviation that you look to see if your data comes from a sample or from a population, because what you divide by in the formula is going to be a little bit different depending on which one you're working with. Okay. Also, the symbols that you use would be different too. Okay, now what else do we have in section 3.2? Well, sometimes you want to compare data sets. Now, if the two data sets have the same units, you can just compare the standard deviations directly and say, oh, this one has more variation, this one has less variation. For example, if a rental car company finds that the mid-size cars have a standard deviation of 42 miles driven per week, while full-size cars have a standard deviation of 35 miles driven per week, the mid-size cars have more variation since 42 is bigger than 35. Okay, both data sets have the same units, miles driven per week. So you can just make a direct comparison. But what if the two data sets have different units? So what if we say the mid-size cars are driven an average of 500 miles per week with a standard deviation of 42 miles, and the company spends an average of $1,000 in vehicle maintenance on a mid-size car with a standard deviation of $64. Which data set is more variable? Which data set has more variation in it? Well, you can't just compare the standard deviation for the miles driven with the standard deviation for the cost of repairs because they're two different units, miles and dollars. It's like comparing apples and oranges. So in order to make these comparisons, okay, like I said, we can't just compare dollars to miles. We have to calculate something called the coefficient of variation in order to make this comparison. Now, the coefficient of variation is just the standard deviation divided by the mean. So for a sample, it would be S over X bar, and then multiply by 100% to convert it to a percentage. For a population, sigma is the standard deviation over mu is the mean. And then you multiply by 100%. So for the maintenance cost here, $64 standard deviation divided by $1,000 mean times 100% would give you 6.4%. For the miles driven, 42 standard deviation over 500 mean times 100% would give you 8.4%. So the miles driven data set is more variable than the maintenance cost. Even though 42 was smaller than 64, when we kind of change the units so that we can make a direct comparison here, we see that it's actually the miles driven that is more variable. Okay, and one last thing I want to go over with you, really two things, but they're related. It's called the empirical rule. So for normal data I think I've already described to you, is data where the histogram would have that bell-shaped kind of curve, Okay, so you get this nice symmetric histogram where you could fit a bell curve right over top of it. It turns out that the mean for normal data is right in the middle. And if you were to calculate the standard deviation for this data, and on a number line, take a step to the right that is equal to the standard deviation, so that would be your mean plus 1 standard deviation, and then take a step to the left, that would be your mean minus 1 standard deviation, 68% of the data values will be in that range. Now, if you were to take 2 steps equal to the standard deviation above the mean, so that would be the mean plus 2 standard deviations, and go 2 steps below, which would be the mean minus 2 standard deviations, 95% of the data will be in that range. And if you were to go 3 steps above and below, then 99% of the data would be in that range. Okay, so you can see that if we were thinking about where the numbers in the data set fall, 68% of them would be clustered within 1 standard deviation of the mean, 95% within 2 standard deviations, and 99% would be within 3. Only 1% of the data would be outside of that 3 standard deviation range. Now that's for normal data. If we don't have normally distributed data, if the data is distributed in some kind of other way, then we have to use Chebyshev's theorem to get an idea of what percentage of the data is within so many standard deviations of the mean. So Chebyshev's theorem says that at least 1 minus 1 over k squared times 100% of the data values will be within k standard deviations of the mean. Okay, so for example, if I say k is 2, this formula, known as Chebyshev's theorem, will tell me what percentage of the data is within 2 standard deviations of the mean. So if I put 2 in for k, 1 minus 1 over 2 squared is 1 minus 1/4, which is 3/4, and that's 0.75 or 75%. We could say 75% of the data is within 2 standard deviations of the mean. That's true for any distribution. Now remember, for normal distributions, it's 95%. Okay? With normal distributions, we can say that it's not just 75, but as much as 95% is within 2 standard deviations. But we don't always have normal data, so sometimes we have to use Chebyshev's theorem. Okay, so let's say we had some test scores where the average was 72.6 and the standard deviation was 3.7. We could say between what 2 values did 75% of the students score? Well, we just found out that 75% of the students will be within 2 standard deviations of the mean. So here's the mean, 72.6. Go 2 steps below the mean, so that's minus 2 times the standard deviation, you get 65.2. And then take 72.6 plus 2 standard deviations above the mean would be 80.0. So you could say 75% of the students scored between these 2 values. Okay, so that's Chebyshev's theorem. That applies to any kind of distribution. But with normal distributions, you can say a little bit more with the empirical rule. Okay, so that's some of the highlights from section 3.2. In our next video, we will finish up chapter 3.